All right, we might as well get started. It's my pleasure today to welcome David Rutledge, who is the Chief Technical Officer at Lattice Semiconductor, an important FPGA company. David spent his first part of his career at Harris Semiconductor building one of the very first programmable logic devices, a bipolar PAL, and has been in the programmable logic industry ever since then for, if I calculate correctly, 32 years. Is that right?
Sounds good.
For 26 of those years, he's been at Lattice, taking it from a very tiny company, your employee number 31, and has risen to the point where he's in charge of thinking about the future. David.
Thank you, Jonathan. Welcome, everybody. Am I in a good spot here? Good. My pleasure to be here, and I'm very happy to see the broad turnout here. I've been in the industry since 1976, and I'm looking around the room here, and I'm thinking there aren't many people here that were born in 1976. But I remember when I was sitting in your chairs, listening to the guy from Hewlett-Packard or wherever it was at the time, thinking, wow, he is a genius, and I'm just a poor university student. But I assure you, you have long and glorious careers ahead of yourself. It'll be a real interesting time in the next 20 years or so. So, I appreciate everybody stopping out today. I've got a lot of slides and I'm going to go really quickly. Some of them are pretty detailed, and in the interest of time, I'm not going to spend a lot of time on them. We could probably spend 3 or 4 hours here. So I wanted to take the opportunity to come visit the University of Toronto and get Lattice some exposure to the professors and the students and the research that's going on here. So that's part of the exercise today. Also, part of the exercise is to tell you a little bit about what we see from the industry perspective in this domain. And I also appreciate everybody stopping in today on a Tuesday instead of a Thursday. I think the normal FPGA seminar is Thursday, so this is a special case. So I appreciate that. So I'm going to talk about a few different topics today. We'll go as quickly as we can. First, I will give a brief obligatory corporate advertisement, if you will, corporate overview. Call it advertisement. Many people don't know who Lattice is or what we do, so I'll cover that. Then I want to talk a little bit about more, and more than more, and FPGA market expansion. I assume everyone here is familiar with the term Moore's Law. Anybody want to define that for me? Your chance for audience participation? Okay, we'll talk a little bit more about it when we get there. A little more about it when we get there. All right, so to begin with, corporate overview. Lattice is in the programmable logic business. One of our main focuses is low power and low cost. So many people associate FPGAs with very high power, very high cost, very high density types of products. Lattice tends to focus in the low power, low cost area of the FPGA market. So a slightly different market focus than some of the bigger competitors. We've been very successful. In the last 10 years, we've sold over 1 billion programmable devices. So we've been in the business since 1983. As Jonathan said, I joined Lattice in 1983 as the 31st employee. So we've been doing it for a long time. We're a worldwide organization. I won't spend time on this slide, but we're exposed around the world. And a brief timeline over the past 10 years in terms of some of our innovation. The only thing I'll highlight here is that over time we've expanded from a CPLD company to a non-volatile FPGA company, adding mixed signal products, SRAM FPGAs, and SoCs. So we continue to add to our product portfolio, and that's all I wanted to cover there. As I described earlier, we focus in a certain part of the market here, in this case mid-range FPGAs and low-density PLDs, not necessarily high-end FPGAs. So Xilinx and Altera will build some very high-density products. We build products slightly below that point. This is just an example of some of the products that are in our product line. You can go to our website and see these anytime. So won't spend any more time on that. That's just a little bit about who Lattice is. Now, in terms of more, now we'll talk a little bit about semiconductor technology evolution. We'll talk about Moore's Law. It does continue to drive functional integration, and I've got highlighted here, I'm going to build this slide pretty quickly. 1970s, before many of you were born, There was actually a time when semiconductor companies owned their own fabrication facility, and we were putting about 3,000 transistors on a chip. When I built my first chip in 1976, I think there were about 10,000 transistors on it. I hand-laid each one of them out and measured them with a ruler, and I tell people I knew every one of the transistors personally, and every one was unique and different, just like your children. That was a time when everything was handcrafted. It was a pretty interesting part of the business. By the 1980s, integration levels were growing up to about a 3 million transistor chip count, or transistor count, and we were adding more complex functions like adders and ALUs to the chips, and these were pre-built IPs of that domain, 4-bit adders and that type of thing. And again, one company built all of those products. They had the fab, did the design, did the technology development, design, and product development. By the 1990s, a new model had evolved. The foundry model evolved because it became too expensive for semiconductor companies to own their own fab. And so the foundry model developed, and standalone foundries began developing the wafers and the process technologies, and new fabless semiconductor companies were built on top of the foundry model. So now we started building more complex functions and building more complex IP, and the fabless semiconductor companies, of which Altera, Xilinx, and Lattice are all models. In fact, in 1983, Lattice was one of the first fabless semiconductor companies in the world. When I went to work for the company, we had intended to build our own fab, and 6 months into it, we said, it just isn't going to work, it doesn't work anymore, we've got to go with a foundry. And we built one of the first foundry relationships in the semiconductor industry. Soon thereafter, many other companies started doing it. It was an interesting time when you didn't own your own fab, because the world said you will never succeed if you don't own your own fab. And today it's a very different world. So by the 2000s, now we're approaching 3 billion transistors on a chip. The foundries are growing and adding more functionality, capturing more functionality, and IP development, IP development and now SoC integration is coming to the forefront. And so the fabless design guys are moving up the food chain, the foundry guys are further moving up the food chain. In this decade, by the end of this decade, we'll be talking about 100 billion transistors on a chip, if you can imagine that. The foundries are still doing their thing, but now there's a new industry evolving between the foundries and the system integrators, and that's the IP industry. Because these IP blocks are getting to be so complex, it's a standalone development and a standalone product that companies are making. So now there are IP companies and an IP industry evolving between the foundries and the system-on-chip integrators. So this is what the world looks like today. The system-on-chip guys are still trying to do some of the IP, and the foundry guys are also trying to do some of the IP, but the bottom line is there's a new industry emerging in between those two. And ultimately, the IP guys may be consumed by a foundry guy. Who knows? Today's standalone business. So, along the same lines, package complexity over the years has grown exponentially, as well as the software complexity to support these types of products. But the message here is today we're building SoC scale devices, whereas once we built gate level devices. So it's a very, very different industry today than it used to be. So, this is a chart that illustrates Moore's Law. Now, some people will tell you Moore's Law is the following. Every 2 years, transistor count doubles. Okay? And if you follow that logic, the blue line on this chart is that progression. So from the 1980 time frame, when we were putting about 100,000 transistors, today in 2011, we're at about the $7 billion transistor mark. Now there's a red line on this chart. Anybody know what that red line is?
Number of transistors you can actually light up?
Nope, but that's a good guess.
Maximum power density?
Maximum power density? No. You had a guess? You know the answer. Yes. Everyone in this room is living at a very special point in time, because This is the time when the transistor count on a single chip is bypassing the world population. There will never be another time when this happens, and you were here. 7 billion people on the face of the earth, 7 billion transistors on the biggest chip we can make today, and I can tell you who's going to win this race, or it's self-evident from this chart here. So, so by the time you guys are finishing your career way out here, you can do the math. It's a pretty scary concept. 1971, this is what the Intel 4004 looked like, and you can actually see separate transistors and wires and things on that chip. Here in 2010, the Intel Sandy Bridge, you can't see much of anything except a lot of blocks that are stepped and repeated, so you can clearly see modular design and reuse on the latest technology, and that is the only way that we build the types of chips we build today. Now, for those of you who really want to know what Moore's Law is about, this is the original Moore's Law page from Gordon Moore's notebook. And it doesn't say transistor count doubles every 2 years. What it says is, at any point in time, there is an optimal number of transistors you can integrate on an integrated circuit for an optimal cost. And if you try to integrate too many transistors, it becomes too expensive. And if you try to integrate too few transistors, it's also more expensive than what you could get out of your next technology. So over time, from 1962 to 1965 to 1970, he is projecting the optimal transistor count increases over time. But this is the real Gordon, or the real Moore's Law theory, is the optimal number of transistors increases over time. So let's talk about Moore's Law a little bit more. It is continuing, but it is slowing. So from 90 nanometers to 65 nanometers to 45 nanometers, you get a normal progression. The semiconductor industry has been on 2 years per node cycle for many, many years. And everything, 90 nanometers, 65 nanometers, 45 nanometers, silicon gate technology. Once we got to 45 nanometers, the rules changed, and we had to develop some new technology to continue Moore's Law. That technology is HighK metal gate technology. And I'll explain a little bit more about that in just a minute. Anybody here or everybody here heard about HighK metal gate? Understand it? Okay, we'll talk a little bit about it. It allowed us to continue down to the 32 nanometer node. However, at 32 nanometers and beyond, the game changes again, and actually we're now moving to about 3 years per node. The ITRS, the International Technology Roadmap for Semiconductors, which is an industry consortium, is predicting we're going to slow to about 3 years per node simply because it's becoming more and more difficult to scale the technology. So the HighK metal gate, we'll talk a little bit more about that. It got us to 32 nanometers, which is kind of where we are today. In order to move to 22 nanometers and 16 nanometers, we're talking about three-dimensional transistors, things that are referred to as FinFETs, silicon on insulator technology. So this is the next step, and bottom line is the transistors will no longer be planar in the silicon. Today, every transistor is planar. You implant dopants into a planar wafer. In the future, we're actually going to be etching the silicon wafer, leaving vertical silicon fins, and building the transistors completely around the fins. And so you will actually get higher transistor density, but it's not going to be planar. It will be in a three-dimensional sense. So this is how we're going to continue Moore's Law, because we can no longer maintain the planar integration. But it is going to slow. So one of the reasons Moore's Law has been so good to us over the years in the semiconductor industry is because it brought great things. Every new technology brought you half the cost. It brought you half the power. It brought you twice the speed. Everything got better as you scaled. That's no longer the case. So the semiconductor industry today is is facing some very difficult challenges in terms of why do we continue to scale? Can we afford to continue to scale? And there are new challenges occurring here. I'll describe a few of those here in the next few slides. So I've got a few metrics here on the left-hand side: gate density, die size, which correlates to cost. The smaller your die, the lower the cost is. speed increase, dynamic power, static power, and signal delays through metal wires, the RC delays of metal wires. Historically, things got much better. 20 years ago, everything was much better. You get twice as many transistors per node, half the power, twice the speed, half the dynamic power, no static power whatsoever in CMOS 20 years ago. And this may be news to the world, but there was a time when CMOS was a zero static power technology. And signal delay was increasing at about a 1.2x per node, the RC of the metal system. Today, everything has changed. One thing that hasn't changed, you're still getting twice as many transistors on the chip as you did in the previous technology. So I give that one 3 arrows up. However, the die size shrink is not so great, and therefore it's a marginal incremental benefit. The speed increase, ID sat of the transistors, is not as good, 20% per node. It gets a marginal upside there. Dynamic power reduction, not as much as it used to be. We're not voltage scaling. We're not doing as many things to reduce dynamic power. So that's a marginal improvement. However, at the bottom of the list here, 2 things are getting much worse. The static power is increasing exponentially now, and I'll explain that in a minute. That's why we're going to HighK metal gate technology. And the RC delay of the metal system on the chips is also increasing by a factor of about 2x per node. So these are major downsides. So at the end of the day, the benefits of scaling relative to the downsides of scaling are becoming far less of a win to move to the next technology, coupled with the fact that to go to the next technology, every new technology is now costing exponentially more to develop because of the complexity. So it used to cost $10 million to develop a new technology. Today it costs $10 billion to develop a new technology. So the bottom line is the wafers on each new technology are increasing in cost, and the die size used to shrink faster than the wafer cost increase. So if your die size shrinks faster than the wafer increases, then your overall die cost is going to be less. If you get twice as many die and the wafer costs you the same thing from one node to the next, it's going to be half the cost to go to the next node. But if you get twice as many die and the wafer costs you 4 times as much on the next node, it's actually costing you twice as much per die to go to the next node. So the point here is you may actually increase your product cost by going to the next technology. The only fundamental reason to go to the new technologies now is the top line here. If you need more gates than what your current technology will give you, you must go to the next technology to get that. But otherwise, some of the other benefits are far less compelling. So, being in the commercial industry and in a for-profit industry, these are things we look at when we develop new products. We look at these things very closely, and the industry looks at this because there's got to be a reason to develop the new technology. So I'm going to spend some time talking about each of these things. In terms of the gate density, what used to happen from 130 nanometers to 90 nanometers to 65 nanometers, we'd get a 50% die size shrink every time we went from one node to the next. Today, that's no longer the case. And it's largely the case because the I/O ring is a large part of the overall product. The core area will shrink by a factor of 50%, but the I/O ring and pad ring doesn't shrink by that much. So at the end of the day, you end up getting about a 25% shrink from one node to the next, and similarly going to the next node again. So now it takes you almost 2 nodes to get the 50% die size shrink that you used to get in one node. So this is an important consideration. Now, another thing that's happening is something called restrictive design rules. And this is required at sub-wavelength geometries. The geometries we're trying to print now are actually smaller than the wavelength of the light being used to create them. And so they use optical tricks to produce the geometries on the wafer. So this is something I think everybody's familiar with in terms of classic layout in 65 nanometer or older technology. Just jog your poly, jog your diffusion, do whatever you want to do. In 28 nanometer and beyond, everything is very orthogonal. Everything is unidirectional. Unidirectional poly, no right angles, no orthogonal turns. And this is an actual die level photograph of a 28 nanometer chip showing that kind of thing. So you can see the packing density does not is impacted by your inability to do the jobs and things that you used to be able to do. So again, this talks to the fact you don't get a 50% shrink from node to node anymore, and you have to do this or you cannot print these geometries. The light will only focus one direction, and it will create a blurry edge on the other direction. So you have to do things in a unidirectional fashion. So it's quite a graph theory issue, quite a graph theory challenge for the people laying these chips out. It doesn't show up in your schematics, but it shows up in your layout. So let's talk about static power now. This is becoming dominant at 65 nanometers and beyond, and this is why we had to move to HighK metal gate. Basically, gate oxide on these devices at 65 nanometers is only a few molecular layers thick. And it's no longer being an insulator, it's no longer acting as an insulator, it's actually becoming conductive. And so there are a number of different sources of leakage, and there are two fundamental sources of leakage in a CMOS device that are getting exponentially worse, that need to be controlled. One is the channel leakage, this I sub S component, drain to source leakage. Basically, we can't get enough electric field into this channel to turn the carriers off, to turn it off hard. And even when you turn the transistor off, there's still some leakage that occurs here. And as you scale the voltage supplies and scale your threshold voltages, this increases exponentially. The other source of leakage current is gate leakage, and that's leakage directly from the gate into the substrate through the gate oxide, and that's because of the thin gate oxide. So we have to thin the gate so that we can control this subthreshold leakage here and control the channel, but as we thin the gate, then we start to punch through the gate itself into the channel. And so this is an actual TEM of a cross-section of one of these gate regions, and you can see the silicon dioxide area here, silicon gate area below the gate and above the substrate. And these dots here are actual silicon atoms. This is now about 6 atomic layers of oxide. And so you can see going from 6 to 5 is a significant decrease. And at 5 atomic layers, basically it's no longer acting as an insulator. It's just going to punch right through. So in order to continue to scale the technology, we had to do something about this gate oxide, because we must scale the oxide, and yet you can't scale the oxide and have it be electrically insulating. So the gate oxide material had to be changed. Now let's talk about what's happening here. And again, this is from the ITRS, and this talks in terms of the green line being the technology trend from quarter micron here. These are feature sizes, 250 nanometers or quarter micron, down to today's region of 32 and 28 nanometers. So you can follow the green line down. And here's two leakage characteristics: gate oxide leakage and subthreshold leakage. Back on the previous page, that's this gate leakage here and the channel leakage here from source to drain. And what you can see is this is power dissipation on a log scale, and you can see this leakage is, both leakages are exponentially increasing as we scale the technology. This is a train wreck out here. We won't be able to continue to develop the technology if we stay on these trends. And furthermore, the gate oxide was getting to be the dominant characteristic in terms of power. So you can see many examples of this in products that you buy today, but certainly state-of-the-art technology is a reasonably high-power technology. So enter the HighK metal gate transistor. It replaces the silicon gate oxide with a hafnium-based gate oxide. It's a different material, and it essentially it has a higher dielectric constant. So what you can do is you can make that material thicker, and it will be electrically insulating, but it has the same electrical effectiveness as a thinner dielectric of silicon dioxide. So you get the benefit of, it's the high dielectric constant, which is why they call it HighK. It couples more directly to the substrate and gives you better electrical control while still being able to be a thicker material. So again, looking at the real geometries here, this is the previous transistor we looked at. This is a HighK metal gate. You can actually, instead of having 12 angstroms of oxide, you can have 30 angstroms of HighK hafnium-based gate oxide, and even though it's thicker physically, it is electrically thinner than the silicon dioxide due to the dielectric constant. So this benefits you in terms of improving subthreshold leakage by coupling more directly to the substrate, and gate leakage by having a thicker dielectric that will not punch through and allow leakage current into the substrate. So this is, when you hear the term HighK metal gate, every technology beyond 65 nanometers is using it, and this is what it's all about. Now, in terms of orders of magnitude, subthreshold leakage is reduced by about a factor of 5. Gate leakage is reduced by orders of magnitude, 10 to 100x, because you are significantly thicker here. So, what does that do for you in terms of this chart? It effectively resets these two leakage characteristics and drops them down close to an order of magnitude, and you're now back to a point where you can continue to scale the technology and have reasonable power levels. It doesn't fix anything, it doesn't make it go away, it improves it and lets you continue to make progress for the next few generations. There's still, we're still going to get back up to this level a few years from now and have to deal with that. Now, in terms of, I won't spend a lot of time on this, but this is basically an Intel IEDM presentation where they're showing the same thing. This is gate oxide scaling, and gate oxide scaled by a factor of 0.7x for every generation up until 130 nanometers, after which we could no longer make the oxide thinner because it would punch through. So we resorted to things called strained silicon, which I won't go into, but that helped buy some time and the HighK metal gate, but it didn't allow us to make the, to scale the oxide. HighK metal gate now allows us to pick up on oxide scaling again and continue to go down from there. So it just allows us to continue the trend that we've historically had. All right, let's talk about speed. I just talked about static power. So I've talked about die shrinks and technology scaling. I've just talked about static power. Now let's talk about metal RC. It's more than doubling at every node. Here you can see the capacitance in terms of femtofarads per micron from one technology to the next, and relatively flat over time. The resistance of those metal lines, however, as you can see, is increasing substantially because we are thinning the metal in terms of making it narrower to fit tighter pitches. So the resistance is a function of the width of the metal, and you can see it's more than doubling every node. The ratio from here to here is 3x, from here to here another 3x. So these are the ratios, and the total RC ratio over 2.8 along the way. At 28 nanometers, we've slowed it down to about 2.0, but nevertheless, your metal is beginning to dominate in terms of the delays. It doesn't matter how fast your transistors are if you can't get through the metal. Let's talk about the anatomy of a modern FPGA. Speed, power, cost drivers here. This is a metal stack. There are 15 layers of metal illustrated there. Down here at the bottom, there's something we know as transistor. Now, again, 30 years ago when I started in the industry, I started in the industry with one layer metal. There was a time when all we did was one layer metal. And over the years, we figured out how to stack more and more metal on top. But the fact of the matter is, the transistors have continued to scale, and they're now relatively insignificant to the metal stack. Many ASICs today use about 7 layers of metal. They don't need too many layers of metal. 7 is plenty sufficient for most applications. An Intel 32 nanometer microprocessor, the latest Ivy Bridge processors from Intel, 9 layers of metal. Current FPGAs, 11 to 12 layers of metal. Why? We need routing. Everybody needs routing. Future FPGAs, maybe 15 layers of metal. That's a pretty amazing load for a little transistor down here to carry. And so you can see the challenges. The RC time constants associated with this stack grow. It becomes more and more difficult. So scaling your transistors, even if you can make your transistor twice as fast, it doesn't make your chip twice as fast by any stretch. It's all about, you've got to balance your metal system as well. So let's talk about speed, power, and cost drivers. From a static power standpoint, it's all in the transistors. As I described earlier, it's right here. And it's gate leakage and subthreshold leakage. has nothing to do with the metal stack. Static power doesn't care about the metal whatsoever. So if you want to make a low static power device, you've got to do it with your transistors. From a dynamic power standpoint, it's all about voltage. Dynamic power is CDF power. The capacitance, as we described in an earlier chart, isn't really changing that much from node to node. The frequency is an application level issue, and we all know that's going up. The only way to deal with this is with your voltage. So we've got to continue to scale voltage. So that's the primary driver for future technologies, is scaling the voltage. Speed is actually becoming dominated by the metal, not by the transistors. So transistors are still critical and important in the process, but if you ignore your metal, you're not going to be a winner. You're not going to be getting the most out of the product. So that's the message here, is if you want to talk about what's controlling your speed, you need to pay close attention to your metal system. And we may need to be changing the metallurgy in future technologies. And finally, when we talk about speed, power, and cost drivers for FPGAs, LUT density is one of the things that drives both cost and power. Now, why is that? Well, if you use a lot, the higher your LUT density, the more routing you need. And the more routing you need, it drives the cost, because you need more metal layers to do the routes, and it drives the silicon area, because you've got to put transistors on every one of your multiplexers and routing switches. So higher LUT density means more routing, means more silicon area and more metal layers. Routing also drives static power consumption for the same reason. More transistors and muxes will lead to more static power consumption. So Lattice's focus has been on low-cost, low-power FPGAs and mid-range FPGAs, not high density. And we've opted to not build the highest density devices, because higher density will imply higher cost and power. So that's our particular market focus. But this is a key trade-off. If you want to build low cost, low power, LUT density, you can't go to the highest LUT densities and balance that equation. So there you have it: static power, dynamic power, speed, and cost in terms of FPGA careabouts. So this is just a summary slide. We've talked about all of these, and again, I think I've made the point here. Gate density is the only real reason to go to the next technology node. Now, if you're in the processor business like Intel is, or the GPU business like NVIDIA is, they can't get enough cores, they can't get enough this, they will always go to the next node. It always benefits them, but you have to be very thoughtful about that when you make your decisions. Okay, more than more. SoC plus SIP. Anybody here heard the term more than more? Paul? Vaughn? Okay, and Jonathan? Guys who are close to the industry, I guess. All right, so the more than more term recognizes the fact that Moore's law isn't going to be the only thing that drives the industry in the future. We've got to do something more than more. So what is that? Again, from the ITRS, Moore's law will continue to scale, and we're going to go beyond CMOS at some point to some other technologies, nanotubes or other technologies, quantum devices. But beyond that, there's a lot of functional diversification going on that has nothing to do with monolithically integrating more transistors and more functionality. Things like analog functions, high voltage and power, passive sensors, biochips. These are not necessarily monolithically integrated with a semiconductor, but they are part of a system and part of a product that people want to sell to the industry. So what is basically occurring here is there's a combination of two things that are happening. One is the digital content per chip is increasing, and that's the system on chip vector. And the non-digital content is increasing as well, and that's system and package, by putting multiple technologies together in one package. So package technology plays into the functional diversification. This is how the industry sees us going beyond Moore's law and continuing to add more value and more integration. So I won't bore you with this slide. You can read it, but this describes what the ITRS refers to as more, and then more than more. So you can read that at your leisure. graphically, the system in package concept is illustrated here, and I'm going to give Xilinx credit. They created these diagrams, and I thought they were useful, so I borrowed them. I hope they don't mind, and I know you don't. At any rate, the traditional multi-chip module approach basically puts a number of separate components together on what amounts to a PC board, a small PC board. There are long traces and slow and not high density traces. What we're moving to is 2.5D and 3D technology, where we're basically we're using what's called a silicon interposer, and this is a silicon die that has metal traces embedded on it. It's basically a small semiconductor chip itself, but it's just metal traces, and you can then mount two separate die on top of that and get much higher signal density and much higher signal performance because we can print metal lines at semiconductor chip level densities. So one step in the process is to put chips side by side on a very high density, what's referred to as a silicon interposer, and put high density interconnect between them. Finally, we'll ultimately go to 3D, where we will actually be connecting from one chip to another chip directly below it. And we'll be drilling through the chips and interconnecting directly through what's known as TSV, through silicon via technology. So this is actively in development right now, and these technologies promise to add significantly greater functional density and performance levels. You can talk in terms of multi-gigahertz signals being transmitted on these types of chips, whereas here you have a much more difficult time. So this is a cross-sectional view that would show multiple FPGAs and RAMs sitting on top of a silicon interposer that are interconnected with very high performance local interconnect, and then that interposer is then placed on a PC board or in a BGA package, a classic BGA package that has less dense signal interconnect and lower performance interconnect. So this is one side-by-side placement, and then here you can see the vertical stacking that's coming in future. So this is a graphical illustration of the more than more concept, system in package as opposed to system on chip. Okay, now we're going to switch gears and talk a little bit about market expansion. Everybody's familiar with an FPGA that looks like this, right? You guys have seen things like this? 2-3 inches on the side, weighs about 10 pounds, costs about $800 or something like that, right? Burns 50 watts. Okay. Yes? No? Okay. So Lattice is looking at a slightly different market here. We're looking at the consumer mobile market. Everybody's got a cell phone, everybody's got notebook computers, tablet computers. There's a huge emerging market for portable consumer devices. And the challenge is, in going to these portable consumer devices, this probably doesn't work too well. Not gonna see one of these in here probably. Certainly not in your cell phone. Interestingly, you see the unit volumes are growing exponentially. Literally billions of units here with smartphones, tablets, e-readers, you name it. The volume in the consumer mobile marketplace is immense relative to the PC market. The PC market is small by comparison. So what's the care about here? Well, a couple of care abouts here in terms of power. The desktop machines consume watts. Your mobile devices consume milliwatts and microwatts. So the care about is low power. The care about is low cost. I've got to be in the dollars, tens of dollars, not hundreds of dollars to play in this market. So another way of looking at that is consumer mobile FPGAs, which is something Lattice is interested in developing this market, have got to have low power, they've got to have low cost, they've got to have some embedded hard IP to do some basic functions that the system guys need, and they've got to be a very small footprint package. So Lattice has developed the Mach X02 family to address this market. And I won't go into the advertising here, but the bottom line is static power as low as 19 microwatts, not milliwatts, microwatts. Low cost, small packages, 2.5 millimeters on a side. I'll show you what that looks like in just a minute. Low cost in terms of sub $1, in terms of sub 50 cents for an FPGA. Wide range of reasonable lookup table densities and integrated functionality like I2Cs, timer, counter, and SPI interfaces. Just a few standard system level interfaces. This is the product line. I won't go into the detail here. 256 lookup tables of very low density FPGA, less than 1,000 lookup tables, up to about 7,000 lookup tables. The important thing is here, 19 microwatt standby, up to 230 microwatt standby. So very, very low power, very, very low cost. This is the FPGA. There you see it relative to a nickel and a dime, if you can see it there. 25 ball wafer level chip scale package. Basically that package is the same size as the die. We just put some epoxy on it and then put balls on it. So 25 balls on this package. This is what it looks like in close up, and you can see here around the outside, this is actually the edge of the die. It's just been scribed, and these are the bond pads on the die around the edge, and you can see we've only hooked up a few of them because we've only got 25 balls that we can hook up. So the die actually has hundreds of pads on it, and we've hooked up 25 of the most important pads for the customer. This product is going in cell phones as we speak. And the way the guys are using it is as a control application, as a control PLD, and everything is done serially. So you don't need hundreds of IOs to run things massively parallel. Basically, we're running a serial interface, either I2C or SPI, and all communications, they bring data across serially, process it in the chip, and then ship it out serially. And the device is fast enough to meet the speed requirements of the application.
David, how
Yes.
many of the 25 are power and ground?
About 7.
Okay.
About 25% of those are power and ground. And we've got a JTAG interface that's using 4 of them. Got to have JTAG. They're only about 10 or 12 I/O on the device. Yeah.
Okay.
So I have a package here, and I'm going to pass it around. This actually has some of these packages in it. I'll pass it around here. Be careful. You'll lose them. But there you can see a consumer mobile FPGA. Those little shiny spots in there are one of these die. So much different than this package right here.
So that's the smallest package, or actually all devices in the family is packaged like that?
That is the smallest package. That's the 25 ball. We also that's the 12. Actually, that's the 1200. It's not a 256. It's the 1200, but that's the smallest package. And then we also offer the 2000 in a slightly larger package, a 49 ball package. But that's what the technology is capable of today. So 19 microwatts, 2.5 millimeters on a side, 50-cent cost, and put it in your cell phone and buy as many of them as you want. So how do we do this? So a couple of things we've done to manage power, and we're running out of time, and I'm pretty close here. I think we'll make it. Just a time check. If we need 5 minutes extra, have we got that?
Yeah, and that clock is 5 minutes past, actually.
Oh, that's a Rutledge clock. Okay, good. Set just for me. Okay, so basically, one of the things that we've done in any low power semiconductor chip, you probably want to have a modal state architecture where you have an on-chip power controller so you can turn things off and on as needed. Now we've implemented 3 modes of operation. The normal mode of operation, which is full on power, normal use operation. We have low power options where things can be dynamically shut down when not required. So you don't send the part into standby, but if you don't need the PLL, turn it off. If you don't need if you don't need the on-chip oscillator, turn it off. That type of thing. And then we do have an ultra low power standby mode where everything is turned off except for monitoring the system standby signal, and the system can bring the part out of standby. So basically, this goes to the lowest power state. This is where you get your 19 microwatt standby, is when you get to the standby state. So it's a very simple state machine. There's really two fundamental states to it. And the reason I highlight this is because we're attacking the power problem from an architecture standpoint. I'm also going to talk a little bit about the technology standpoint in the next couple of slides. But architecturally, there's really two states, about two modal states. There's the operational state and the standby state. The other two states illustrated in the state machine are simply getting into standby cleanly and coming out of standby cleanly. So these are transition states just to smooth the transition. Basically, you're either operating or you're in standby, and in standby we turn a lot of things off. Very simple design. It's not a 32-bit processor that we're using to control the power. It's a simple 4-state state machine. Now, some of the things that we do for both static and dynamic power down options, there's a number of things on the chips that typically consume power, so we give the customer the option to either statically or dynamically turn off certain features. The band gap is one thing. Most chips have a band gap on them because we need reference voltages and currents on the chip, and the band gap consumes some current itself and some power itself. So if you don't need the things the band gap controls, you can turn that off. We have an on-chip oscillator that we can turn off statically or dynamically. Either turn it off statically if you're not using it, or dynamically when you're not using it. PLLs on the board. I/O bank controller. There's a number of I/O standards that require references. Differential signaling I/O standards typically require some reference voltage. So the I/O bank controller generates those reference voltages, but it consumes power. If you're not using a reference standard, you can turn that off. We've got dynamic clock enable on primary clock net. So if you're not using a clock net on the chip, we can turn that off. And a power guard feature, which is an interesting feature. Not many people know it, but when you're sitting in a system, even if you turn your chip off, if other chips in the system are toggling and inputs on your chip are being toggled, those are consuming dynamic power because they've got input buffers that are switching when the input switches. So even if your chip isn't doing anything with those signals, there's dynamic power being consumed. So we've got a feature that on a pin-by-pin basis can allow people to turn off an input completely and have it ignore all inputs on that pin and not consume any dynamic power, even if the external signal is switching in the system. So that's an interesting feature that we've added. So these are all architectural features that we've added for power optimization. Let's talk a little bit about the process technology. This is something we also spent a lot of time on because the best architecture in the world is only as good as the fundamental process technology it's built upon. So we've talked about this diagram before. There's a number of sources of leakage. I'm going to reiterate here. Gate leakage from the gate into the substrate through the gate oxide. Subthreshold leakage, drain to source leakage, this direction. And bulk drain leakage, which is leakage from the drain diffusion into the substrate. Just the PN junction here will leak. So those are three major components of static power consumption in any technology. And I just highlight here the gate leakage is controlled completely by the gate oxide thickness. The thicker it is, the less it is, the thinner it is, the more it is, and that's an exponential relationship as you get to thin oxides. So 1 or 2 angstroms can be a factor of 10x difference. So tuning that gate oxide is very important. Subthreshold leakage is inversely proportional to the threshold voltage. So the drain to source leakage here, the lower the threshold voltage, the higher that leakage. And again, that's an exponential relationship. A tenth of a volt or 10 millivolts of threshold voltage can be a 10x increase in subthreshold leakage. So again, it's very critical in terms of where you set your threshold voltage. And importantly, as you scale your supply voltages from 3 volts to 2 volts to 1 volt, you need to scale your threshold voltages. So we used to have threshold voltages of 1 volt on transistors. Today we're operating with threshold voltages of 200 millivolts and going lower. So that's part of the reason subthreshold leakage is becoming dominant. And finally, the drain leakage is a combination of a number of subtle features, junction leakage and gate-headed breakdown. I won't go into those too much, but those are the three leakage components. I'll tell you what we've done in each of these areas. So, the first thing to highlight here, the first component, the subthreshold leakage. This really doesn't depend on the process details too much. It is basically just a function of the threshold voltage. So the lower your threshold voltage, the higher the leakage current, and you can see that illustrated here. And again, the exponential relationship I described, a linear change in threshold voltage translates to a logarithmic change in subthreshold leakage. So this characteristic, I'm just going to illustrate that with this slope right here, and we're going to look at the next component and see how it reacts as a function of threshold voltage. The drain leakage, interestingly, is inversely proportional, and actually it increases as higher threshold voltage. So this is a number of different process technologies, but the basic trend is increasing threshold voltage will actually increase the leakage current as well. So that's a bad thing. So this is really bad because at higher threshold voltages you not only get slower, but you get higher static power. You slow down because of the high threshold voltage, you get higher static power because of this drain leakage characteristic. So when you put those two together, you actually find there is a reasonable minimum when you combine those. So in terms of getting the lowest static leakage on a process, you want to optimize your subthreshold leakage and your drain leakage and get to that lowest point. So the way you do that is to raise your VT, start down here at a low VT, and by the way, today's technologies, I should say, let's go back to this one. Today's technologies are running with about 200 millivolts of threshold voltage. They used to be about 500 millivolts, but as we scale the technology and scale supply voltages, everybody's going this way, and so threshold voltage is dropping, and this is what's causing this parasitic or this characteristic to become dominant in terms of leakage power. So when designing a low power FPGA, you actually want to increase your threshold voltage and get away from this subthreshold leakage characteristic, but you can't go too far because then you run into the drain leakage component. So the idea is go raise the VT as much as possible and then do something with your drain engineering to move this drain leakage from here down, and then you can continue to scale your threshold voltage up, and you keep doing that successively until you get to an optimal point in terms of your leakage characteristic. Now finally, the gate leakage is an independent variable, and it really doesn't have a temperature dependence or a process dependence other than the thickness of the gate oxide, as we said. And so what you want to do is, if you get to the point where the gate oxide leakage is going to become dominant, if you go down much further, what you want to do is you increase your gate oxide thickness so that your leakage goes down, and again you continue to scale and get lower static leakage overall. So it's a balancing game, optimizing these three parameters to make a very low power transistor process. And that's what we've done for our low power FPGA, and that's in direct contravention to a classic FPGA, high performance FPGA, which is going to be sitting over here, and none of this stuff matters because it's completely dominated by the subthreshold leakage. Now, finally, the interesting thing that we did here, and this is something we've applied for a patent on, and this is something that all the students in the room and the researchers, everybody will appreciate, is how do you get two different speed power characteristics out of one physical design? Can you make one transistor design and get two different speed power characteristics? The answer is yes. If you build an inverter, you can set the threshold voltage of the transistors at ½ volt and get a certain speed power characteristic. You can set it at ¼ volt, drop it by 50%, and you'll speed the thing up and get higher power. So at an inverter level, everybody can understand if you change the threshold voltage, you get a different speed power characteristic. But can you build an entire product and an entire circuit that you don't have to change a physical geometry, a W or an L or any design parameter, and just implant it differently and get two different speed power out of it? That's what we did with the X02 family. So we have one threshold voltage target that is the absolute lowest static power. And what I've got illustrated here, by the way, this purple curve is essentially static power consumption. And as you can see, as a function of threshold voltage, there's an optimal point after which it starts to increase again. The orange curve up here is the operating frequency, or how fast will the chip go. So this is speed and power. And you can see at low threshold voltage, you can get relatively high speed at a significantly higher power level, or if you go to higher threshold voltage, you can get a very low static power at a somewhat reduced operating frequency. Importantly here, the power scale is log, and the operating frequency scale is linear. So we built a product that you could implant with one threshold voltage and get the absolute lowest power at a reasonable speed, but implant it at a different threshold voltage, set a lower threshold voltage, and get a 2 to 3 times faster part, but it will cost you 100x power, or put another way, you can get this part, and if you want 100 times lower power, you can drop down here and pay only a small speed penalty to get that. So this is an interesting thing. It's the first time we've ever done anything like this. First time in the industry, I think, I've seen this done. And the fact is, if we go back, I'm going to go back many slides here. So if you go back, every one of these parts has 2 different speed power options. We've got the low power option here, which is 19 microwatts, and then we've got the higher power. Let's pick this one. Let's pick the 2000 here. Let's say this is a 98 microwatt standby power part, or we can go to the high performance version, which is 2 milliwatts. So we're going from 100 microwatts to 2 milliwatts, 20x difference in power, and we basically get a 2x speed improvement in doing that. So we actually built one mask set that can be processed in the fab with 2 different threshold voltage implants and get a high speed, higher power option, or a low speed, very low power option without touching the mask set and without making a new design. So we actually, and the reason we do this is because there are different application markets. Some customers care more about the speed than the power. They say, I need twice the speed and I'm willing to pay a milliwatt in power. Even at 2 or 3 milliwatts, these are very, very low power parts relative to classic FPGAs. But if you want to really operate in the handheld market, you've got to have the microwatt power level. So we implemented that as well. And I think that's probably it. Yeah. So in summary, I guess what I would leave you with is the semiconductor industry is certainly facing technology challenges moving forward and continuing to scale the technology and add speed and add power and still reduce cost. It is becoming exponentially more difficult. There are a lot of challenges, and hopefully a lot of people in this room are going to be solving those challenges moving forward at a semiconductor technology level. In terms of the consumer market, I think most people here are familiar with FPGAs and their use in high power, high performance systems, much less so in low power, low cost systems. And that's a domain and a trend that Lattice is interested in pursuing. We see great opportunity in that area. And as a matter of fact, I was telling Jonathan earlier, the MacBook Pro here on the desk. Does anyone else here have a MacBook Pro? It seems to be a popular computer. That's got one of our FPGAs in it. And most people would say FPGAs don't go in computers, but there is a Lattice FPGA in every MacBook Pro. We're driving the video display for those of you who are interested. So anyway, I think there's a good opportunity in exploring low power, low cost opportunities for FPGAs. That's something that we're also interested in working with the universities in researching and moving that technology forward. Thank you.
A little bit of time for some questions.
Sure. I can't imagine there were any questions after that. I figured that explained everything. Yes.
So you've gone to a foundry system, but it sounds like you still need a process development group?
Less and less. The foundries, the industry is moving toward a standard process model, and you use what the foundry has available. So, you know, it's Burger King and McDonald's. Burger King, you get a Big Mac. McDonald's have it or rather have it your way, you know, Whopper with or without cheese or whatever, and McDonald's is you get the Big Mac and that's all there is. So it's moving to a Big Mac model or a McDonald's model where it's on the menu and don't ask for anything special.
But this last thing that you just talked about, that sounds like your development, not a foundry.
Well, the foundries are interested in developing low power processes, sure. and the important thing is you do want to try to work with them during their process and technology development to influence their development, but if you get there after the fact, it is what it is. Yes?
So the whole mobile market's very high volume, and you care about power a lot. So what actual cases would there be where you'd want to use a low power FPGA as opposed to perhaps even lower power ASIC for these mass-produced things?
Well, the fact is that, and that's a really good question, the fact is that FPGAs can actually be as low power and low cost as an ASIC. And that's what's happening is in the world today, building an ASIC is an extremely expensive process. It used to be $50,000. Today it's $5 million or $10 million. Even small ASICs can be very expensive. So there's a big NRE associated with doing an ASIC. And if the FPGA can get competitive on cost and power, there's no reason to do the ASIC, and that's where we are right now. So I mean, an ASIC isn't going to be much lower power than a 19 microwatt type of level. Yes?
Sorry, kind of a related question. I noticed your smallest FPGA only had a couple hundred LUTs and no RAM. So what are your customers typically using these little things for?
Yeah, again, the low density stuff is used for glue logic, garbage collection, small state machines. A lot of the, FPGAs again, the classic big FPGAs typically used for data path applications. You got DSP and all kinds of data processing going on. And lots of memory, lots of need for that, but it's a data path application where people are using the low density FPGAs. They're actually control applications, and there's just a few state machines. You typically want a lot of I/O because control applications want to have fingers into a lot of places, and they'll even use it for things like lighting an LED and monitoring a button for a push and that type of thing. So control applications tend to want to have lots of I/Os, but in certain applications, and so this is a very I/O intensive device, but we've also packaged it in a low I/O, small footprint package for applications that don't need those, and those types of applications are these low speed serial control things. So again, in the cell phone, they're actually using the FPGA to do more than control. It is actually doing some data processing, but it is not a compute intense thing that needs DSP or lots of memory. So it's basically the applications tend to be more control as opposed to data path. Probably the best answer to your question. Yes?
What size of FPGA do you have in the MacBook Pro?
That is one of our XP2 devices. It's an XP2, which is a non-volatile FPGA. And by the way, I didn't make a big splash on that here, but we actually build non-volatile FPGAs, which instead of being SRAM based and have to be booted from somewhere, we have an embedded flash process where we store the code on chip, and so the part boots itself, and it comes up very quickly in the customer system, much more quickly than an SRAM FPGA. But the answer to your question is this is our XP2 5K. So it has 5,000 lookup tables. It's got some embedded memory blocks. It does not have any DSP. And it's in a 132 chip scale package. So it's got 132 balls on it, roughly 100 IOs.
Are you looking into seriously at asynchronous logic to minimize the dynamic side?
The question is, are we looking seriously at asynchronous logic to minimize some of the power, dynamic power? And the answer is no, we're not looking at it seriously. Are we aware of it and considering it? Yes, but there is no serious activity there.
Who is your foundry?
Our current foundry at 65 nanometers is Fujitsu in Japan. And that's what the X02 is built on, a 65 nanometer technology. And as I said, low cost, moving to the next node is not always the best thing for low cost. And the X02 devices being low density, they don't need an advanced technology. And at 65 nanometers, it's actually a much lower cost product than it would be at 45 or 28. So we've chosen 65 for that product. Yes.
Follow up on Paul's question, essentially, do you have any rights in those processes that you're developing with Fujitsu, or could anybody else come and try to use them too?
We have some proprietary developments that we've done with them that are co-developments that they don't have the rights to pass on to customers, but for the most part, the processes are available to other customers. this low power process we're talking about, I honestly don't know the answer to that question. I'm not sure what the legal agreement is there. Yes, Mark.
Physically, how large are the bigger devices? You have a 6,000 watt device. Like what would the package size be for that?
It's still very small, like 3.5 millimeters by 3.5 millimeters. Yeah, it's very small.
So you talk about the design trade-off that you have to make in order to reduce the cost of the FPGA, right? So I also noticed that Xilinx 7 series, it seems to make the decision that all families seems to adopt the same design.
Yes.
So I'm just wondering whether you have a comment on that. So.
Well, that's an interesting trade-off, and we have lots of conversations about that. The question is that cost is typically optimized if you can optimize your architecture for a particular density, and Xilinx's latest Series 7 family spans a large density, and they're using what's called a platform technology where the same architecture is applied across the family. And so, can I be optimized at the high end, high density end, as well as at the low density end for cost and other factors? And the answer is we don't think so, and that's the price you pay for the modular approach and get the family out quickly, because if you use a building block approach and make everything out of one set of blocks, you can get the whole family out pretty quickly. And that was Xilinx's priority in the Series 7, was get things out quickly. And I think they knew they would pay a little bit of price in terms of cost and power on the low end in order to do that. And that's why Lattice competes relatively effectively there. They win at the high end. We're not trying to compete there. We can do a better job at the low end where they're suboptimal. But they're still quite competitive.
So they're just cutting down the margins.
Yeah, exactly. Yeah, they'll sell the lower density parts at lower margins, and they get whatever they want for the high end parts. So it's a business management trade-off there.
Great. Well, thank you very much.
Okay.